Okay, so the last, I decided to do something simple for the last lecture. So about clocking, invisibility, how to make objects invisible. This has been a subject of interest to humans for a long time, at least since Greek mythology, Perseus versus Medusa, science fiction, movies, etc., etc. So let me show you a trailer with some clips from movies, certain recent, not recent movies. 1 second, let me come back. Sorry. Okay. There's no sound. It's supposed to be sound. Well, you have to imagine that there is some sound. Why there is no sound?
Invisible man is in my house. He's mad. We go gathering nuts and pay on the
Let me see.
It's not showing up on the screen.
It's okay. It's okay.
And also, I couldn't connect your screen to that.
Oh, it's, huh? Oh, I make a mess instead of.
Yeah, I made it.
Yes.
Have you tried these ones?
Technical problems.
think if you just pull out the HDMI and put it back in.
But
Out of there. Is that working? Because then sometimes it just automatically routes it. Okay, and then if you plug it back in, and then just
in the meantime, you can use this one to
No.
give some explanation. And I call the tech support.
Mm.
Yeah. We touch something and then the computer changes.
So it should be the laptop?
Yep.
pay attention.
So yeah, we wanted to get sound also. Try everything.
Yeah.
So I think somebody made very special
Yeah.
configuration here, and I lost the main screen. So the other day when I asked actually the tech guy could control the
Okay, let me go. Get one mic a better design. But
Maybe take this out and put it back.
I was controlling from the other. Yes, I so first so Gunther would like to play the movie with sound. Sound didn't work. I touched something and then we cannot go back to it.
If you have another laptop, they can one can play the sound, one can play the movie.
Well, I think that's
Like
not
that.
the problem. So HDMI already sent the sound
Right.
signal here, so I don't know how to control this. Yeah, we have to wait. But in the meantime,
Sorry about that.
So in the
I
meantime, you
cannot,
can use this
no,
mic
not for this.
but sure. So that's using the fancy image. Yeah, sorry.
Now slide is invisible.
No, because no, it were playing, it was showing, but I touched something here. I cannot come back to the audience setting.
So we wanted to get sound, but I don't see if it's. I should.
Can you just make it?
The movie won't play.
I got to do this at the office. I'm gonna go around it tomorrow.
So we are trying to copy your
Yeah, but it won't work. It won't work.
Why not?
when you transfer the movies don't work in other computer.
Why not?
I don't know.
But we cannot play movie, but the other part.
Yeah, there's a lot of movies.
Then you can copy the movie file from the
Can you see? Well, you can try to see. You see
Yeah.
them.
Are there movie files on your computer?
No,
But
no,
why-
no, they are embedded. They're embedded.
Embedded. Then it should work if they're embedded.
I have experience.
Well,
laptop should have
he says it's embedded in the PDF.
okay, then if we copy the PDF, then we copy it.
That's what I'm saying, but he says he has experience that it doesn't work. So we can try it and see if it works. Do you want me to send it?
But what's the difference?
Do you want me
when
to
they
send
use-
it to you?
We already have the
We
file.
have it.
It doesn't have. But this is a page for movie, but that's
Oh,
not
I
it.
see.
See.
So I can search for the movies on
No,
it.
this, I don't have it there. No, it's not there. It's not there.
It'd probably be in the same.
No.
Or
This-
you can
this
open the
is-
PDF file. Next page. Oh, so movie should be.
Which one is the movie?
I think this is a movie.
This is the movie?
No, there's the first one.
Where the
Just wait for the person to see.
Invisible man is in my house. He's mad. We go gathering nuts and bear.
I told you. That's what I said. You can play it on this.
You can look at it. Should be.
Can you guys see?
But you know,
They all say yes.
how about the other parts of the file?
The next movie.
There are a lot of formulas and stuff.
You have to find that chapter
Huh?
We didn't.
The image is here.
Strange. Yeah, let me see.
So, well, sorry.
Actually, the size was there. It's big.
You can come here and look at it.
That thing is bigger than
It reminds me of the old days before all of you were born, where you were in the middle of a movie, and then all the lights went out, the screen disappeared, had to wait for hours sometimes for the movie to come back. Supposed to be high tech nowadays. Too high tech. It's on the other side now. So full screen. Okay. I think you have to go down. Over here.
Just wait for it.
It's even better.
It's worse.
Partially invisible.
In fact, that ain't a problem.
University of Uhlmann,
Clemson is now in one more.
Clemson, Washington. He's taking a photo there.
Visibility my office notes for me.
What's happening?
Go to the next page, see what it is.
That's the movie. The movie's not there. English problems.
No sound.
That's okay. I should have insisted on the sound. That created a lot of problems. Sorry? But the problem is the image now. Maybe I will give you more problems, open problems. What are you looking at? It's half invisible.
You can see the individual pixels. And you can see the RGB little elements on these pixels. So for those who are interested in how monitors work, I suggest coming afterwards and looking at the pixels.
Try and unplug this and unplug this.
Huh?
You have to do an inverse transformation on the screen to realign it.
Except for
It's shifting.
squash.
It's shifting. Looks like.
At some point that we could see the full video on the left pane.
I could try that, yeah. I can
That's also
try
fine.
switching
We
over to
need
that
just
one.
screen looking.
See if I can get one. I did do that. Yes, I did do that. Yeah, one of the guys reassigned all of the things, and now we're like.
My dad was talking about this. He said that I think problems first try to return.
Okay. Sorry. Okay, so let's see. Well, I'm not going to insist on the sound.
You can still try,
Try what?
but turn the sound to your computer like we had before.
No, let's skip.
You want me to try?
No,
So without sound.
don't try anything. Okay. So invisibility is coming. So the first clip was based on the famous novel by H.G. Wells, Invisible Man. The Invisible Man was a chemist that made himself invisible by changing his index of refraction to make it look the same as of air. Now, the way you see is by the reflection of light in your eyes. And so if the index of refraction is the same as of air, then he's invisible. You see the clothes because the clothes reflect light. And then you can see that. So this procedure is not recommended. And actually the Invisible Man tried to reverse it. And it's unlikely to work because the human body is very heterogeneous and the index of refraction changes a lot from different tissues. Yes. So my son pointed out to me that the comics, I think the Fantastic Four, where there is the Invisible Woman by Susan Storm Richards, and she makes herself invisible, as you saw in the clip, you see, by creating a field of energy around her. And we are not told how to do that, how she does this, but the idea is to deflect light. Again, the way you see things is by reflection of light or scattering or some process like that. And if light is deflected around her, then she's invisible. Okay, so this is a good idea, deflect light. And the Invisible Man also has a good idea, which is change the index of refraction. But of course, not that way. And a little bit more scientific way of doing what the Invisible Woman was doing is done in the clock Romulan Bird of Prey in Star Trek. So this ship makes itself invisible because it has gravitons on the surface of the ship. Gravitons produce a very high gravitational field. And in Einstein's theory of relativity, you have a very high mass, gravitational field, space-time will warp, and light will be deflected. And so this is more scientific at least. But of course, how to do this for electromagnetic waves, we don't know how to do this on Earth. So the way it can be done is through a cloak, a la Harry Potter. So what we are going to try to create is a cloak of invisibility in such a way that has an index of refraction that makes light go around. And so, therefore, you don't see because there is no reflection of light. So this is me half invisible. So I had to make a demonstration, so there it is. You see Maxwell equations on the back, on the background. Another one, my hand invisible. Okay, so the scientific idea behind invisibility has been called transformation optics. It's a fancy name for something very simple. And we found it by finding some conductivities that could not be detected by making electrical measurements. We have studied Calderon problem quite a lot. So this was non-uniqueness for Calderon's problem. And this was published in the Institute of Physics journal, a more, without proofs, description of the idea, anisotropic conductivities that cannot be detected by EIT, electrical impedance tomography. So already this is given out, it will be anisotropic. And in 2006, there appeared two articles in Science, Controlling Electromagnetic Fields by Penry et al. And in the same issue of Science, a related article in Dimension 2 using conformal mappings. So this was called optical conformal mapping. So it's the same idea that we have here. Penry had actually not only the same idea, but the same transformation. And this article had a lot of publicity and has about 10,000 citations. But the transformation, as you're going to see, is exactly the same. The idea is exactly the same. Okay, so Science magazine has a very good description of the method, the ultimate camouflage. The real breakthrough may lie in the theoretical tools used to make the clock. In such transformation optics, researchers imagine Einstein warping empty space. This is what you want to do to bend the path of electromagnetic waves so that the waves will be deflected and go around the object that you want to make invisible. Mathematical transformation then tells them how to mimic the bending by filling unwarped space with a material whose optical properties vary from point to point. So this is changing the index of refraction. You're going to make a clock that has a special index of refraction that makes light go around. The technique could be used to design antennas, shields, and myriad other devices. Any way you look at it, the ideas behind invisibility are likely to cast a long shadow. Of course, you don't want a shadow, because if you have a shadow, you can see something of the object. Right? You can see the projections or light. You can get some information. No shadow, no scattering, no reflection, nothing. From all directions, this is another important thing. So this is a cartoon. This is a cross-section of the clock. In the blue is the clock, and in the red, in the orange ball here is Harry Potter, in this ball here. And then the light comes in. These are the rays of light, and they go around the object. And when you measure it outside, the clock looks like the light went straight through, like in the Invisible Man. So you have the two effects, the invisible man, invisible woman, at the same time. Right? And what we did in that in the paper I mentioned was to do this for conductivities, which are electrostatics. There are waves in electrostatics. The arrows are the currents. On the left is current the currents for conductivity 1, homogeneous, or any constant conductivity that goes straight through, like the vacuum. And we construct the conductivities so that the currents go around the object, but when you measure it outside, it looks like the same measurements as the picture on the left. So you cannot distinguish between the picture on the right and the picture on the left. And any object that you put here inside is invisible to electrical measurements. Because these currents go around, you cannot detect anything that you put here by making measurements outside. Okay, so as I mentioned, as in the description in Science magazine says, there is an analogy with the theory of relativity. You have a large mass, like the sun, and here is the Earth. When you see a star, it's not in the position that it is, because light is deflected. This is a gravitational lensing that we talked about yesterday. But astronomers use gravitational lensing to detect where the star is actually is. Of course, the opposite effect of what we want, deflecting light, is a black hole. So black hole, after you pass the event horizon, light is trapped and cannot get out. That's why it's called black. And so this is an effect. We want to create the opposite effect to a black hole, although creating an optical black hole is something of interest to make experiments in laboratory. What we want to create is an optical white hole, so the light goes around, and so this object is invisible. It's a white hole because you're not trapping light, you're deflecting light. So there is a theory of light which is very, explains a lot of effects that you can see, which is the rate theory of light of Fermat's principle. I think I mentioned this before. This is the index of refraction varies from low to high here. And light or sound or waves in general try to go from one point to another in the minimum amount of time possible. So because the time is related to the velocity of light in the medium, in this case, the rays of light are not going to go in a straight line. Like it will be if the index of refraction is uniform, they will be deflected. So light takes the shortest optical path. So these are actually geodesics, since we already know this, of a metric. You go along the geodesics of a certain metric. The certain metric is related to the index of refraction the same way that we had before. So one is the speed of the medium is c. This is the metric. And then you're taking the geodesics. Oh, can you see this? Now it's in the middle. There's not much space. But you can see this. Then this is the index of refraction squared. The index of refraction is the inverse of the sound speed. So this Fermat's principle explains many things. For instance, you have the air and water have very different index of refraction. And in order to go in the minimum amount of time possible, light will break. This is a problem you can give to your calculus students. Find the curve that minimizes the time to go from one point to the other, or the distance. So when you see a fish, certain position is not there because light has broken. That's the effect that you see also in a glass of water. You see the straw broken, but it's not broken, just an illusion. Invisibility, of course, is an illusion. There is something there. We are going to arrange it so that you don't see it. So this index of refraction actually occurs in nature, in the mirage. It's very hot near the surface of the desert, and I'm sure you can see water when you're going on the roads in Clemson, because it must be very hot in the summer. And then, the light will go up because of the index of refraction, and then when you think you're seeing water, you're actually seeing the sky. So the ray theory of light explains many things, but not everything. For instance, diffraction, refraction, and things of that sort are explained by the wave theory of light. And there is a question of whether it's not just the rays, whether you can do full wave clocking for waves, electromagnetic waves in particular. Light is an electromagnetic wave. So this is the wave theory of light. This is Maxwell equations. You have an electric field and a magnetic field. So the electric field is in red here, magnetic field is perpendicular here. And there are the electromagnetic parameters, is electric permittivity, and magnetic permeability describes the electric magnetic property of the material. And the connection with the index of refraction is the square root of epsilon times mu. This was found by Maxwell. And this is the Maxwell equations, one of the great triumphs of civilization. If I have to take something out of the earth before it collapses, I will take Maxwell equations. So this is time harmonic. So you're assuming that you have a wave of the form e to the I omega, kt. So when you take Maxwell equation, there is no time here, there is the frequency, because I want to relate it to the frequency. So these are called time harmonic Maxwell equations. D is the electric displacement, E and H is the electromagnetic field, B is the magnetic displacement. And this is, again, the electromagnetic parameters and the index of refraction. Of course, Maxwell completed the equations. There were Gauss laws and so on. And there were the famous experiments of Faraday. There were many previous work. It was not just Maxwell, but he completed the equations. When I was teaching vector calculus, I explained to the students Maxwell equations. And I said, you're learning calculus so you can understand these equations. And the students ask, is this going to be in the final? That cooled down my interest in teaching. So the electromagnetic parameters, in the case, I'm going to give the answer of the electromagnetic parameters of the clock. And they're going to be anisotropic. Anisotropic means that epsilon and mu are matrices. And crystals, for instance, are very anisotropic for Maxwell equations. And that means electric displacement is not in the same direction as the electric field, and the magnetic displacement is not in the same direction as the magnetic field. And they're going to be related to geometry. It's again the same fact that we have for the conductivity equation, that Maxwell equations are invariant under changes of coordinates. So you change coordinates, you will get new Maxwell equation, new mu, new epsilon and h, but they will be of the same form. The equations will be exactly the same form. The cross product here and so on. And there will be the same relations here. The divergence equal to 0. There is no density of current here and no magnetic monopoles. Okay, so this is it will be of the form G inverse. This is not going to be positive definite, but will be semi-positive definite symmetric matrix. And this is something we already have seen before. Square root determinant of G times G upper ij in the Laplace-Beltrami operator. This is invariant on the changes of coordinates. It's the conductivity equation. Remember that was crucial to show that there is this change of variables that leaves the equation invariant and the problem invariant. And so this is true also for the Helmholtz equation, which I have separated the electromagnetic field here. This is the Laplace-Beltrami operator, is a Laplacian, the metric is identity. We have seen this before. And for the case of Helmholtz, there is a k-square here. For Calderon's problem, it's the electrostatic case, k equal to 0. So this is Calderon's problem. And you have harmonic functions here. Okay, so this part I'm not going to do. This is part of a talk I gave recently, because I was explaining. You know all of this, right? About Calderon's problem. If you don't know, you don't get reimbursement. And this is the idea of transformation optics. Remember, the problem is invariant on the changes of coordinates. Most physical laws are invariant on the changes of coordinates, should not depend on the coordinate system in which you are looking, right? So this is physical space. So you want to make invisible, the blue fish is in this ball here. And what we want to do is make the rays of light deflect. On the left, there is a rays of light, which is a straight line. There is a Cartesian system of coordinates here. We're going to change coordinates. How are we going to change coordinates so we have this effect? We're going to blow up this point to the ball. So this point will be expanded to the ball, or the other way, the ball will be contracted to the point. And why do we do that? Because the point is invisible. You cannot see a point. So this corresponds by the transformation to the point. So therefore, this should be invisible if the laws of physics are invariant in the transformations. You can take other things than a point in 3 dimensions. The curve is invisible also in 3 dimensions. The technical condition is the Hausdorff dimension is less or equal than less than 1. But anyway, this is a point or a curve are invisible in 3 dimensions. But we're taking a point, so you blow up a point. That's it. That's all the theory of transformation optics. So this is what the transformation is doing. So you take the point, you can see the Cartesian system deflecting here. That's what you want to do, deflect light. So this is the transformation. You can write it explicitly in this case. You take the ball of radius 2. The only difference of the paper, of Penry and our paper, was that we took the ball of radius 2 and radius 1. They took the ball of radius R2 and R1. Because that's the novelty. So this is the transformation, and this is a change of variables away from 0, of course. 0 is not a diffeomorphism because this is not equivalent. A point is not topological or differential equivalent to a ball. So this is explicit transformation. It's identity at the boundary. This is what we want, and the inverse goes this way. So now I can tell you the conductivity of Harry Potter's clock. You take the identity on the ball here on the left, the identity, conductivity 1. It's isotropic. Then you take the push forward of this conductivity by this map away from the point. So on the annulus, that's the conductivity, the push forward of 1, or the identity. That's on Harry Potter's clock. And inside the ball of radius 1, inside the region you want to make invisible, you can put another arbitrary positive definite symmetric matrix. Any conductivity that you like, positive definite, anything. Okay? So this is an arbitrary positive definite on the ball. The theorem is, and this is the, by the way, this is the conductivity of the clock on the annulus here. The blue region that we had before is the push forward, and we can compute it explicitly, and in spherical coordinates in dimension 3, it's given like this. You can see it's not positive definite because r equal to 1, r is the radius. That's where the boundary of the clock is, or the region you want to clock. This is the ball of radius 1. It vanishes of order 1. This is in a region where the sign is not 0. It's diagonal, it's anisotropic, but we show that the Dirichlet to Neumann map in spite is not positive definite. This is a very simple singularity. In fact, it's what Iran called a conormal singularity at r equal to 1. You can define the Dirichlet to Neumann map. That means all the electrical measurements is the same as 1, conductivity 1. Yes? It's continuous. Or up to here, up to the clock. And here it may have a jump. Inside it's arbitrary positive definite, but up to here it's continuous. So it varies continuously in the clock. But here is not, it changes, right? It can be anything. So it had to change here. It's L infinity. It's bounded and measurable. In the what? Yeah, it's continuous. You mean in r equal to 1? Where? This one? Here? But it's identity everywhere. 1 is 1. I'm pushed forward in 1. Right? Sorry?
It's not the identity in the center at all.
In this ball here, no. It's a push. It's arbitrary positive definite matrix. That's what we want because we want to clock anything. Any conductivity that you put, we don't want to see it. It's the opposite of what you do in inverse problem. We want, in inverse problem, we're trying to hide, find something. In invisibility, you try to hide it. It's the other side of the same coin, right?
You can do the same thing for like radical light.
Yes, yes, I want to get to that. The same, is the same transformation. And this is the theorem. So there is a theorem that tells you that the measurements are the same. All the electrical measurements are the same. It's not just, the experimental fact, it's a theorem.
There is component of gamma delta
Is-
over sine theta. So
Yeah, this is away from theta equal to 0. You are away from theta. I wrote it, you can also write it in Cartesian coordinate. I wanted to point out that the r equal to 1, this is degenerate. And this is the picture that I showed before. The electrical currents go around, but when you measure it outside, it looks like it went straight through, like conductivity 1. And you can draw the currents because we know exactly what the conductivity has to be. And you can also do acoustic clocking for sound waves. This is something that was done ad hoc in the Second World War. So the sound speed of the ocean is related to how cold it is, to temperature. So the submarines have a sensor to tell them at a certain particular height where they were, where it was colder. And the temperature is related to the index of refraction. So there will be here a smaller index of refraction when it's colder, and therefore the rays will avoid the regions of low velocity. And when you have sonar here, they will try to avoid it. Of course, some rays will penetrate, but in general, this is not perfect clocking by any means. But it was a very imaginative way to go undetected by sonar. But you have to have a sensor to measure the temperature. So this can be also done for the Helmholtz equation, which describes propagation of sound. And this is once more is this the square root determinant of G times G upper IJ that appears. Now you have a frequency here. The physical interpretation is different. Before we had conductivity, there was this, the conductivity was this. Now this is the density, anisotropic density, and this is called the Borg modulus. And the metric is the same, exactly the same. It's square root of the determinant of G times G upper J. And the theorem is that the Dirichlet to Neumann map associated to this G is the same as the identity. So you cannot distinguish between vacuum for sound and this particular metric. Again, inside the ball of radius 1, you put an arbitrary positive definite matrix. And this was realized as acoustic clocking also in the physics literature by in these two papers. And you can do it for light, for Maxwell equations. And it's exactly the same principle. You take Maxwell equations, I already for time harmonic waves, and it's exactly the same. This is the answer I already gave you. Epsilon equal to mu is equal to G inverse times the square root determinant of G for the clock. And inside the clock, you put an arbitrary positive definite symmetric matrix. That means a Riemannian matrix. And the theorem is that the Dirichlet to Neumann map in this case is the same as identity. That means vacuum is the same as for this new matrix. And these are the electromagnetic parameters. Now, epsilon is equal to mu. The Dirichlet to Neumann map, by the way, in this case for Maxwell equations, is not that you map the normal derivative of the, because it's a first order system, you map the tangential component of the electric field, mu is the outer normal, to the tangential component of the magnetic field. That's the analog of the Dirichlet to Neumann map in that case. And you have a blueprint. Now I'm going to write it in terms of the radius. Blueprint for the electromagnetic parameters. Remember, epsilon, this is the R component, this is the theta component, this is the phi component, the theta component. You can write it in terms of the radius. So we have a blueprint for the clock. We know exactly what the electromagnetic parameters have to be, therefore the index of refraction as well. And this is the same phenomenon. Here is for conductivity, and these are for the rays of light, but also you want to do it for the waves, right? The waves, electromagnetic waves. And this is for the waves, simulation for the waves. So this is plane waves coming in, and when you serve it on the other side, it looks like nothing happened. So this is invisible to electromagnetic waves. And you can send the waves from any direction. It's not just from the direction that they send them. You can do many other things from transformation optics. Why just to map it to a point? I can make myself look like somebody more handsome. George Clooney, right? George Clooney. This is, of course, this is the sad reality. This is illusion of space. And this is, it's not a, well, it's partly a joke, but this is actually, there are serious papers in the physics literature and the mathematics literature. He did this when he was, it's Hongyu Liu, when he was my postdoc. And I told him to try to do this, and he did it. But you know, in mathematics, we publish much later than physics, unfortunately. It takes much more time to get published in math. You can also do quantum clocking at a very small scale. When I want to talk about, Feynman gave a very famous speech in 1959 to the American Physical Society. It's an incredible speech where he predicted nanotechnology. This was 59. So what I want to talk about is the problem of manipulating and controlling things on a small scale. He said in particular, you can put all the information of the libraries of the world in a pin of a needle. And that turns out to be true. You have that information in your pocket or wherever your phone is. And also you can do clocking. You can manipulate quantum waves, matter waves. And this was realized, right? There are many chunks, some of them here. And he was at Berkeley at the time. Now he is president of the University of Hong Kong. And you will be surprised, but it's exactly the same. This is the Schrödinger equation. This is the potential. I call it the same name as physicists do, V. This is the energy, we call it lambda. This is the Planck constant, H. And the only difference is the physical interpretation. Instead of being conductivity and density, conductivity in the case of the electrostatics, in acoustics was the density, and this is the effective mass, and this is given exactly by the same, exactly the same. Okay. So there is an important question here because what we have is degenerate conductivity or density or electromagnetic parameter because vanishes to order 1 at the boundary of the clock. Remember, the boundary of the clock is R equal to 1. How can we have something which is positive definite? Because we would like to have the material which is positive definite. So you can do truncation, meaning near the clock, near the boundary of the clock, we take whatever we had before here, and here we take an arbitrary positive definite symmetric metric, a little bit beyond the boundary of the clock, 1 plus epsilon, radius 1 plus epsilon. So now it will be positive definite. Will be L infinity, will change, but will be positive definite. So we take the one for perfect clocking up to here, and from here on, we take an arbitrary positive definite symmetric matrix, and we can show, and this is a theorem, that the Dirichlet to Neumann map for this conductivity depends on epsilon, approaches the one for conductivity 1 as epsilon goes to 0. So you get approximate clocking. You don't get exact clocking. 5 minutes? Okay. You don't get exact clocking, but you get approximate clocking. And that's good enough for practical purposes.